Greetings, everybody. How you doing? This is Kinesiology 214, and specific to this presentation, it's a continuation regarding ways to quantify work. And specifically, we're talking about how to evaluate performance utilizing loading parameters in a strength-related environment. So we'll have another video that's going to be more cardiovascular as well as plyometric oriented in terms of touches. This is more specific towards strength training. Now, some of the content you're going to see is going to be a review, but also a reflection and a deeper dive into this content. Earlier, we had talked about tonnage, right? And tonnage was the total amount of weight somebody moves in a particular workout. And that was a way to quantify workloads. And that was done by multiplying the number of reps and sets together, and then multiplying that by the amount of weight moved. Pretty easy to see when you have 3 sets of 10 done at 70 pounds, or 4 sets of 8 done at 25 pounds. But in the real training environment, you'll end up having multiple rep and set combinations with varying rep and set combinations, with varying weight load parameters with different exercises. So it kind of gets a little more complex than that. But specifically to what we're talking about today, this is all about being able to quantify work in a particular workout session or a particular exercise within the context of a session. I did mention in a previous presentation that there are, and I've done this as a strength coach, where I've actually mapped out rep and set combinations over a complete macro cycle of 1 year, and done that specifically in terms of organizing my athletes into particular groups so I can elicit the best training response possible. So we know this if we go back to tonnage, right? You have 3 sets of 10 with 70 pounds. We know that person did 30 reps, and we know they moved 70 pounds with each rep, and the total amount of weight moved was 2,100 pounds. Got it. Totally self-evident. What we didn't translate this over to is this. On the left-hand side, if a person did 3 sets of 10, et cetera, 70 pounds, et cetera, well, we know that at 70 pounds equals 2,100 pounds total moved, right? Okay, so here's the deal. You know that based off our coefficient that we used in class, the 0.03, that coefficient ends up being 0.03 per rep. Now, we did talk about the Epley scale and how that Epley formula slides the scale a little bit. But when you look at this and everything we've talked about with 3 sets of 10 at 70 pounds, it extrapolates out where you know if a person is doing 70% of a floating max, the implication there is that their floating max is 100 pounds. And we did that math in an earlier presentation. That's pretty straightforward. But what happens if the person has a floating max of 200 pounds for a particular exercise? The numbers change, right? You still know it's going to be 0.03, and at 0.03 will carry over to give you 70%. So you've done 70% of your 100 max. Got it. So if my floating max is 200 pounds and I'm doing sets of 10, we know that that's 70%. Well, 70% is 140 pounds. Well, if you're doing 140 pounds in a workout, you divide that by 70%, and that gives you 200 pounds. So the mental gymnastics of math goes both ways. You can do a forward roll or a backwards roll. You can do a somersault forward or backwards. So that holds both ways, but the tonnage now changes, right? So you know that because your floating max is higher, well, every rep you do, you're pushing more weight. Instead of it being 70 pounds, it's now 140 pounds. So your tonnage now goes up to 4,200 pounds. Pretty self-evident, got it. We're using pretty straightforward, easy numbers. And what happens when you get into a person who pushes 150 pounds around or 155 or 160, 165, and those numbers total up, and you can do the math backwards to get you your floating max, but it changes, right? And it changes the tonnage. So that tonnage is constantly changing based off of how much weight you're actually using. So where the heck does all this become useful, right? And what do we use it for? So we start to get into the conversation of how do we actually quantify and qualify workouts? What is very light? What is light? What is medium? What is hard? What is a very hard workout? And those are kind of relative terms, or relative to the person or relative to the exercise that's being done. We'll keep this very simple for this presentation. So you have to look at this and go, okay, well, what am I doing in terms of the exercise? How much weight am I pushing? How many repetitions am I doing? What is the rest in between my sets to allow me to recover? And is this exercise being paired with other exercises? And then further, is it a power-oriented exercise or a strength-oriented exercise? Because those have different effects and demands placed on the central nervous system. So you really need to look at this when you start to quantify workload and compare it to the person that's in front of you. When you evaluate the person, you have to look at how old they are, chronological age, how long they've been working out, their training age, their total body mass, their lean muscle mass, which is also important, the activities that they normally do for their sport or their activity that you're training them for. Do they have other injuries? And there's a few other odds and ends, but for the scope of this presentation, we'll just stick to these main ones here up top. And I always like to refer back to these two. And these two are two individuals that I coached early on in my career. Antoine was a running back. Sully was a lineman. Antoine was a senior. Sully was a freshman. Antoine, by definition, just because of their age and time in school and training wise, Antoine was older and had a higher training age than Sully. Sully came in, he was a freshman. He hadn't done any strength training. There was not a strength training program in his high school at all. And so Antoine was 170 pounds and Sully was 320, and you can see the body fat numbers there approximately, if I remember correctly. But the key component here is when you look at like Antoine, he's able to bench more than 2 times his weight, more than 3.5 times on his squat, and he's able to power clean 1.85 as a coefficient to his body weight. Sully, on the other hand, when you look at it, he can't bench his body weight, he can't squat his body weight, he can't power clean his body weight. So just think of those two athletes, just the picture right there that you're given with that information, those data points. You know Antoine is a vastly different athlete than Sully, and Sully is totally different. And so what would happen if you gave each one of them the same exercise program? We're going to do 3 sets of 10 at 70% for every exercise that we do across the board for an entire mesocycle. It would be wrong to do that, because when you look at this and you look at Antoine and you look at his floating max, you have a 350, 605, 315, and if you asked Antoine to do sets of 10 based off of 70%, here's how much weight he's pushing in total tonnage. And his total workout would be 26,700 pounds. Sully, on the other hand, because he's not as strong, let me get myself out of the way here so you can see this, because he's not as strong, is pushing less weight. And you can see that represented here. His total tonnage is actually less. Now here comes another part of the equation. Antoine weighs 170, Sully weighed 320. Pound for pound, Antoine is being asked to push 3 times the amount of body weight pound for pound. So I have to ask you on this, who is doing more absolute work? Antoine. Who is doing more work pound for pound? Antoine. Does it make sense to have these two individuals have the exact same loading parameters in their workouts when you evaluate the amount of workload that they're doing total and the amount of workload that they're doing as a pound for pound relative strength index per pound of body weight? No. So as a result, you have to give consideration to these variables in here and look at these two different individuals and how they are different body types. And also when you look at this, and I didn't want to hone on this too much, but when you look at the power clean has a higher central nervous system integration component to it. And so you normally wouldn't do sets of 10 with power cleans. You'd actually be like sets of 6, and maybe 7 or 8 would be the high side in terms of like volume for the power clean. So in general, it's a sliding scale. So I would normally not do sets of 10, but I just did this for example in our class. So let's get through this. We got a bunch more slides to go. Now, if we look at this, like this linear progression model, if you remember this from a ways back, you had reps, sets, volume, coefficient. Now I will let you know that these do flip-flop on another slide. I switch them out just so it's easier to see in an example. So you know if you do 3 sets of 10, you're down here at the bottom, 3 sets of 10 reps, you have 30 total reps done. Your coefficient is this because 0.3 times 10 gives you this, and you know you're working at 70%. And so if you go 0.7 times your 30, you get 0.21. Well, okay, if you go 3 sets of 1, your total relative tonnage is 2.91. And this starts to do this to you, right? You're like, well, wait a minute, your total relative tonnage, you're working pretty hard. This starts to beg the question, what is hard? What is light? What is easy? What is very hard? And you start to compare these. And so it becomes a little bit of a brain bender when you look at it, but here's how you can break this out, right? So I switched to sets and reps here. You have 5 sets, 3 sets, 5 sets, or 6 sets. So you could have, for example, 5 sets, but your reps go 10, 8, 6, 4, 2. You can have 3 sets of 10, 5 sets of 6, or 6 sets of 5. It's still 30 repetitions. Okay, all right. And you know your coefficient is different because you have 0.3, 0.24, 0.18, 0.12, 0.6. Okay, now that translates out to, when you calculate it out, here are the percentages you would use for a set of 10, a set of 8, a set of 6, 4, 2. You would use 70, 76, 82, 88, 88, 94. Now, if you look at 3 sets of 10, it's all done at 70%. You do 5 sets of 6, we're going to do straight across. Now, normally I would program this different and manipulate the actual workloads a little differently. And then you have 6 sets of 5 at 85%. So when you look at the total relative tonnage, because you then can take that number and apply it to somebody who has a higher max or lower max, you get an idea of their workload relative pound for body weight. So we know several things from above. When you look at these 4 different workouts, they all have 30 repetitions. The numbers vary from either 3 up to 6 sets, and they all have different total relative tonnages. So when you look at this, you start to quantify this out and you go, okay, well, perhaps the 6 sets of 5 is the toughest one of them all. The one step in this equation that you're not really seeing is you have to look at it and you have to take an average over the 6 sets or the 5 sets or the 3 sets. 3 sets of 10 at the same number, pretty easy. But usually like with 6 sets or 5 sets, you might do a build up. You have 3 work sets, and then you drop the percentages on the last set. And so the percentages won't be exactly 82. It'll be a little bit different. But it gives you a way to quantify your workloads and what is hard and what is easy. So in advanced program design, you have to have this concept of what is light, what is hard, what is easy, what is not. And you have to look at it in terms of the stressors you're placing on the human organism and how general adaptation syndrome is crucial. It's crucial to understand this. And you must give consideration to the person. So it is not only to the person, but you have to be able to understand how much work is being completed relative to that person. Pound for pound, how much weight are they moving per pound of body mass? So that total relative tonnage becomes important because it has a multiplying effect or a dividing effect, if you will, based on the person you're doing the work with. So again, 3 sets of 10 with somebody who's a very, very well-trained, highly trained individual like Antoine might be counterintuitive to do that through an entire training cycle because he's much, much more advanced in those training parameters, the load and volume parameters. It would just be too much for his body, and his body would actually break down. Now, Sully, on the other hand, he needed more of a base. And think back to that cake model, Sully was on the bottom of the cake model, while Antoine was more on the top of the cake model. And so to that end, Sully's still trying to work his base. And with Antoine, we were able to do some cool stuff to really try to elicit a training response and just make him like a firecracker on the football field. With that, I'm going to let that go. I think that's a lot of information in a short amount of time. And I'm certain you guys will have questions on that. So please feel free to bomb me with those. But just realize what you're really trying to do is you're trying to come up with ways to quantify the work that's being done. It's not just random, okay, 3 sets of 10 today, 3 sets of 15. Come up with workload parameters. Try to understand that stressor that you're placing on the human organism, client, your physical therapy patient, or perhaps your athlete, and what type of training response are you hoping to get out of that. When you look at this and you get into advanced program design models, that relative tonnage becomes crucially important. Right now in this stage and for this class, you're good to go with what you have, but realize that becomes a big part of training and training programming and understanding the amount of training load you're placing on the body and how the next column over on that spreadsheet would be total relative tonnage as compared to the person's body weight. And that's a whole nother lecture in of itself. But for that, that'll be another day, another time. Right now, I'm signing off, guys. Have a good one. Bye.